Hello there, it's Keith here, and this is lesson 9 of the YQuest series, and this is the platform-specific lesson for the MSX2. And the MSX2 version is rather fine, you can see it just here. So we got a nice smooth movement here, thanks to the MSX2's VDP, and terrible gameplay by me, as usual. Unfortunately, those graphics don't help me play my own game. But anyway, we got a nice looking game here, and we're going to be looking at the platform-specific code that allowed us to do this. Now, unlike some systems, the MSX2 is a bitmap-based screen, but unfortunately we do have to do VRAM to VRAM transfers. So all of the 8x8 sprites you can see on the screen here are actually stored in the hidden areas of the screen. Now, the screen is 192 lines tall, but the way it works is it works in 256 line tall banks, and the bitmap graphics are all stored at around the 512th line onwards, all in a big sort of block. So that includes all the characters of the font, all the possible frames of animation, and we're going to have to transfer them into that area, and then we're going to have to work out which area of that bank we need to copy to the visible area when we want to draw a sprite onto the screen. It's going to be a bit complicated, unfortunately, but that's the nature of porting a game to systems with different hardware abilities and requirements. Let's go over to the code, let's see what's happening. Okay, so here it is. I'm going to assume you have some understanding of the MSX2, and also you either understand or don't care about the rest of the game, because this example is based on the simple series, the bitmap example and the joystick example originally, and also I'm not going to cover the multi-platform code. I've already done 5 episodes on that, so if you want to see those, take a look at them afterwards. I don't think it's going to make a difference with which order you do it, so if you watch this first, it's still going to make sense. You're just not going to know how the bullet firing routine works or the collision detection works. You're going to understand what we covered today. It's all self-contained. Let's have a look at it anyway. So first we're defining our screen size. Some of the systems have a different screen size, so we've got some common definitions here that reconfigure the multi-platform code accordingly. We need a bank of memory for the variables and the position data and things like that. At the MSX it's C000 by default, so that's what we're using here. Got some common definitions here which just allow me to work with different assemblers. This will compile it with Win8 for the CPC version, you see, and so VASM uses a very slightly different, it uses the include command rather than the read command, so I do have just a sort of bit of compatibility code there. Here we're defining the VDP ports. We're going to need to use those quite a bit, unsurprisingly. Then we've got a generic cartridge header. The cartridge header is built into the code here, so you should just need to compile directly with an assembler. My usual code attaches a cartridge header to the code, but in this case you won't need that because this is a self-contained example, that's why. Next we're turning on our screen here. Then we're initializing our palette register here. We're selecting palette entry 0, and we're then going to transfer all the palette entries to the palette RAM there within the VRAM. Now we're zeroing the user RAM, so everything starts at 0. And then what we're doing next is we're transferring the bitmap data, which is currently in cartridge RAM, in normal Z80 RAM, into VRAM, but we're doing it using this define tiles routine. Now, the MSX2 isn't a tile map, it's a bitmap system, but what my code does is it splits up the bitmap data within the Z80 workspace area within the cartridge into 8x8 blocks, and then it transfers those into video RAM, and it calculates an offset, an X and Y offset, based on 8x8 tiles, simulated tiles, and so we're transferring these to 0. The first 96 will be a font, the rest will be 4 banks of 16 tiles. That's what we're doing, and we'll see the code that deals with that later. Here's the start of our game. We're setting up our lives, level 0, turning off the sound, things like that. And then here we've got the title screen routine. The title screen is a grid of memory that defines tile numbers, and we need to show each of those to draw the introduction graphic. So what we're doing here is we're loading in the tile number, adding 96 because the first 96 tile definitions are our font, you see, and then we're using show sprite to show them to the screen. We're just having to multiply the X and Y position up here so that we've got a byte location, Y line, X byte, and there's 2 pixels per byte because of the screen orientation. Here we're just showing some strings to the screen, high score, the URL for my website, that's very important, and also the press fire message. Here's the start of the level and also the start of a new level. First we wait for fire to be pressed, clear the screen, reset the player position, and then initialize the level, loading in the objects and enemies for that level. And then what we're doing next is we're starting the draw routine. This is going to start looking like the simple series example maybe, and we've got a little loop here while we wait for input, storing in any key presses the user presses in D, And then next, what we're doing here is we are drawing the user interface. That's the score, the lives, the remaining crystals, things like that onto the screen. We then clear the old player position. And what we do next is we're going to start handling the input. Now, with regards to the directions, if we hold down a direction like right, we will rapidly start accelerating, but we don't want to accelerate too fast. So there's a key timeout. If the player holds down a key like right or left, the acceleration will increase, but not increase as fast as it could. So until that timeout reaches 0, we're going to ignore the extra key presses. Here's the actual processing of the key presses. We're looking at each key press button. Here we're looking for up, down, left, right, and we're altering the acceleration accordingly. Here you can see here we're just changing the acceleration as required by each direction. Now, if any direction is pressed, we're setting E. E is going to be the new timeout. We're setting it to 5, so that's how long the keys are going to be ignored until the acceleration will change again. Once we've dealt with the acceleration, we're then dealing with the fire buttons. We're reading in the fire buttons using firmware called D8 here. We need to select a fire button. 1 is fire 1 and 3 is fire 2 here. Fire 1 will fire a player bullet, and that's the multi-platform code. That's the point. You're going to have to look at that other tutorial. And here we're actually stopping the acceleration of the player with fire 2. So if you press fire 2, if you've lost control and you're about to collide, you can press fire 2 and you'll stop very quickly. So that's a bonus for the people with 2 fire joysticks. We're then finally just updating the timeout here with the new value of E, which has been set if up, down, left, right were pressed. And then we are using draw and move, which is the common code that handles all of the drawing of the enemies, the bullets, and the player. So that's the rest of the code. And then finally, we've got the infinite loop, which jumps back up here to the main level loop for the rest of the game. That's really all there is to it. Now, the next bit is going to get tricky. Here we go. So the rest of the code is basically this 8x8 sprite routine, which, as I say, is a simulated sprite. It's actually a bitmap transfer routine, but it does it VDP to VDP, so it has to use VDP commands. If we want to draw a character, first we subtract 32, because there's no characters below character 32, nothing below space. We then load in the X and Y position. Cursor X is immediately after cursor Y, so we load them in a pair. And then we multiply Y by 8, because there's 8 lines per tile. And we multiply X by 4, because there's 4 bytes, 8 pixels per tile. So that's what we do there. And then we run our show sprite routine down here. We've got a show sprite object here, and this will get the sprite frame, multiply that by 16, and then add that to the sprite number, plus 96, because the font comes first. You see, the font is the first 96 defined tiles. And then we're loading the X and Y position from the player's position. Show sprite B is this code just here. Now this is handling the drawing of the graphic to the screen. Now we're using this HMMM command just here. Now where is that? It's down here. Now I actually covered these in an MSX2 tutorial I did recently in the platform specific series. I covered all of the graphics commands of the VDP. I'm only going to go through it very quickly here because I don't want to do that tutorial twice. Basically what this is doing is it's copying an area of video RAM to another area of video RAM. Now the way we're using it is the 8x8 sprite we want to show is in that hidden area from line 512 onwards, and we're going to show it to the visible area. So that's what this command does, and what it will do is it will copy from a source to a destination. And so what we're doing here is we're defining the width and the height of the area to copy as 8 because it's an 8x8 sprite. We're specifying the destination here. We're calculating these from B and C here. We're multiplying B by 2 here. Can notice. And then what we're doing just here is we are calculating the X and Y position of the source based on a tile number. Now the tiles are 8x8, so the width of the screen is 256, and I'm talking about the invisible area of the screen, which is also 256 wide. And we're splitting up the tile number, and so the bits for 0 to 31 are going to be the X position, because we can have 32 tiles wide in that invisible area, and then the rest is the Y position, and we're multiplying those by 8 to get the source position in that invisible area of the screen. I know that's confusing, I apologize, but that's what we're doing. We're having to calculate the 8x8 location from a tile number and convert it to an XY position. So that's working out our source. Our destination is the destination we specified in the visible screen. And then we're using this routine, which will push them onto the stack and then initialize a VDP function call to do the drawing. It's a pain, I know it's a pain, but that's just what we have to do. The blank sprite routine is just using the space from the font to clear a sprite. Get sprite address here, this is just basically to mimic the other functions. What it's doing is it's just calculating the offset within the tile map, adding 96 because those first 96 characters are the font. And here's our bitmap data. Now the font is first, then the 4 banks of the sprite data, and these are transferred into VRAM by the define tiles routine, and it will convert them into tiles within the hidden areas of the screen. Here's our read joystick routine. We're selecting 1, which is the first joystick, 0 would be the keyboard. We're using firmware called D5 here to get the up, down, left and right, but not the fires unfortunately. The fires we're using D8, and we need to specify 1 for fire 1 or 3 for fire 2 as we saw earlier. The wait for fire routine waits for the fire button to be released and then pressed again, and this is so that we can do a level complete kind of message or game over, so that the player isn't holding down fire. While we're waiting for the player to press the fire, we're constantly re-randomizing the random seed, which will just mean there's a bit more randomization to things. Okay. Now define tiles is the companion to this draw both routine here. Now this is taking the data that you saw here and it's transferring it into video RAM, but because the data here is split into 8x8 chunks, we're having to transfer it to video RAM in 8x8 chunks. So again, we're splitting up the data so that we have an X position from 0 to 32, which is a horizontal tile position, and a Y position for the remaining bits of the tile number, and that is the destination within video RAM, within the hidden area of the video RAM. So we're calculating that. We're then setting the width and height again, and what we're doing is we're transferring the first byte of the tile data, which is this data here. We're doing that here, and then once we've done the initialization routine here, we then transfer all the remaining bytes down here. Unfortunately, the way the VDP works, we have to transfer the first byte and then do the rest separately. And this is the routine that's doing the transfer of data from the cartridge ROM, the Z80 memory, into the video RAM. As I say, this was covered in my previous example, the platform specific series, where I went through all of the MSX2 commands one by one, so please take a look at that series if you want to see how that works. There is one other command we're using, and that's for clearing the screen. We specify a start position, a width and a height, which is the full size of the visible screen, a color byte, and we're using black here of course, and then we use this command, and this will just fill an area with a solid byte. So that's our clear screen command. Again, it was covered in that platform specific series. So if you need to see it, please take a look. Then we've got a few commands here to handle processing the status registers to check if the system is ready to take more video data. Again, we're doing that here. There's another one here. There's quite a lot of them. Again, it was all covered in that platform specific series. I say I can't go over it in proper detail again, so please take a look at that episode if you need to see this in detail. Finally, we've got here the definition of the common code. We're using these to do most of our work for the game logic. We've then got the screen initialization here and the palette data here that was used at the very start of our code. So we kind of made a full circle here. There's the palette data just there. And of course, here's the data routine that transferred the tile data from the ROM to the video RAM, which is doing all the work, and that's what's allowing the code to work. Okay, now finally, just to show you what's going on with this video RAM, I've actually loaded up OpenMSX with the debugger here. So you can see here's the visible area of the screen, and you can see that just here. So this is basically what we can see. There's a few extra lines maybe, but then if I select here, lines visible, we'll just expand that to 256. Well, there's a bit here that's not being used. If we then change to page 1, this will be lines 256 to 511. If we then change to page 2, well, this is lines 512 onwards, and this is where I have been defining the pattern data that we will then copy to the visible screen when we want to. So you can see here, here's our font all in nice 8x8 blocks, and then here's the first bank of sprites, here's the second bank, here's the third bank, and here's the fourth. And of course we could keep going indefinitely if we program the code to, and that's why the code was, if I can just get this up here, this is why the code was splitting up into 32 tile wide chunks from a tile number. This is the tile number. This is calculating a 0 to 31 because there's 32 tiles across, and then this is calculating the line down here. But I just wanted to make it clear why we were having to do this weird thing of splitting up the tile data accordingly. But this is pretty good code. It's easy to use and it works quite nicely. So hopefully you can just use this code as is. Well, there we go. Anyway, that's the MSX2 version of the game. All of these are free, open source, and I endorse you to go ahead and modify them. And if you can sell them, good luck to you. You don't need to give me credit. If you've managed to make any good use of them, then best of luck to you. Anyway, I hope you found this interesting in some way. If you have, please like and subscribe, because if you like my videos, then YouTube will hopefully recommend them to more people. Probably won't, but that's all we can do. Anyway, I wish you all the best of luck with whatever you're programming or any other creative projects you're doing. Thanks for watching today, and goodbye.